Okay, so now that you've learned what these, I guess you can say multivariable functions look like, the ones with z equals to f as a function of x and y, now let's talk about trying to do some multivariable calculus. So there's different notations for this too, okay? Now remember here with multivariable calculus, now we have two different independent variables, okay? So when I ask you to figure out the derivative, you have to be more specific. You have to tell me which variable. So if I have dz dx, or the notation is f of x, that means with the definition of the derivative, you're looking at the limit at h approach to 0 of the function f of x plus h. This sounds familiar, right? But this time we have two variables, so comma y minus f of x comma y all over h. Now the idea here is this: we're trying to change the x, right? But what you want to understand is you want to keep now the y variable as a constant. That does not change, okay? That's what this f sub x means, or the derivative with respect to x. dz dy, or f sub y, is really the limit as h approaches to 0 of f of x, and now it's the y value that goes y plus h. Oops. Minus f of x sub y, or x comma y, all over h. And in this case, once again, the idea is you want to find the change in the y value, keeping the x as a constant. So really, you just have to assume now that the other independent variable is like a constant, and just use the rules of derivatives that you learned in AP Calculus. So here we go. Example number 1. If z equals to the arctangent of y over x, I want you to find the partial derivatives of x. That means I want you to find f sub x and the partial derivative of y, which is f sub y. So we'll do f sub x first. This means we keep the x as my variable, make y my constant. So think of it as arctangent of some number divided by x. So the derivative of arctangent, once again, is 1 over 1 plus y over x all squared. Remember that? Hopefully you do. If not, look it up. And then now, yes, you're right, we have to find the derivative of the inside. Now you're thinking, do I have to use quotient rule? The answer is no, because y is a constant. So really, this is like me saying y multiplied by 1 over x. The y is a constant, and now what's the derivative of 1 over x? That's right, that's just negative 1 over x squared. Remember, that's x to the negative 1, use power rule. Okay, so remember this case, the idea is to keep the y as a constant. And this stuff here in the bracket is the chain rule part, because we have a function within a function. Now we should try to simplify this. So I'm saying we have negative y all over, I don't know, let's see what this is, 1 plus y squared over x squared times an x squared. I can simplify this if you want. I think I can make this x squared, so that's x squared plus y squared times x squared. Oh, look, those x squareds divide each other out, and there you have it. Here is my simplified expression for f sub x. By the way, if you're curious what the second derivative would be, that would be f of x, okay? That's the second derivative. I know I didn't ask you for it, but I thought I'd just show you anyways. And in this case, you would then take the expression here, keeping x as a variable and y as a constant, and just find the derivative as well. So if I did it like this, the negative y would be a constant. I can rewrite this as, right, and then x squared plus y squared to the negative 1. So then I can do the chain rule, negative 1 x squared plus y squared to the negative 2, derivative of the inside, which is 2x, the derivative of y squared is just 0, and I can have something like this as my, oops, positive 2xy, my apologies, positive 2xy all over x squared plus y squared all squared. And that would be your second derivative with respect to x. Okay, so these are the partial derivatives with respect to x. All right, that was a tangent. My apologies, but let me go back and just figure out f of, or f sub y, the partial derivative of y. In this case, arc tangent derivative is still 1 over 1 plus y over x all squared. And then we have to use the chain rule. Now think about this now. Using it for f sub y, this is like saying I have a constant 1 over x times y. So the derivative of a constant times y is just 1 over, got it, 1 over x. And then we can simplify this. Same thing, x squared plus y squared all over x squared times x. That equals to 1 over x squared plus y squared over x. Flip it around, x over x squared plus y squared. Done. Okay? So nothing really too out of the ordinary, but now you get to actually figure out derivatives of multivariable calculus. Okay? I'd like you to try example number 2. This time I'm asking you to find an expression here and simplify it. So really I want you to find du dx and then du dt and then plug it into this expression to solve. So let's do that first. Du dx, that would be the derivative of u with respect to x. So the derivative of an exponential function is just the exponential itself. But this time now, think about it. X is my variable. So it's like me saying 1 over t squared times x. Here's my constant. X is my variable, so I'm going to multiply by, yes, 1 over t squared. And if you want to simplify, you just get e to the x over t squared over t squared. Cool? Du dt. Same thing, exponential. This time, however, if I look at the exponent, x over t squared, now I have x as a constant, and then now t to the negative 2 as my variable, constant. So if I were to take the derivative, constant ignore, take the derivative of t to the negative 2, that's negative 2 t to the negative 3. And that simplifies to negative 2x e to the x over t squared, and I'll divide this by t cubed. Okay, so here are our two expressions, and now I ask you to find find 2x times du dx plus t times du dt. So I want you just to substitute all those things in. So here we go. Du dx is just e to the x over t squared all over t squared plus, what colors are those? Plus t. Then du dt is just negative 2x e to the negative, or e to the x over t squared over t cubed. Looking ugly, but nonetheless, unfortunately, what we're looking at trying to simplify. And that becomes t squared. And if you do this, look at that. Adding two things that are opposites of each other give you 0. Yeah. Alright. You turn the page. And I'm going to see if you can try the next example on your own. Okay, at least try it on your own first, and I'll come back and show you. Alright? Go. Okay, so maybe I'll just do the du dx and all those things first. Du dx means x is my variable, so x to the power of y. That means I just need to use power rule. So the y is a constant. Let's bring it down to the front, and I have to reduce the constant by 1, or the exponent by 1. Good. That was the easy one. Okay, du dy, unfortunately not so easy, because now y is my variable. This is like an exponential function. So what's the derivative of an exponential? Yes, it's the exponential itself. But because the exponential has a base that's equal to a constant, if you remember, yes, you have an extra factor of ln x. Good. If you got that far, you're set, because the rest is just pretty straightforward algebra. So here we go. Let's prove this. X over y times du dx. Y, x, y minus 1, plus 1 over ln x times xy ln x. And we're trying to prove this equals to 2u, so notice that these cancel out. I have x times x to the power of y minus 1, plus notice the ln x's cancel out. That's x to the power of y. Hopefully you can see that this is x to the power of 1. So the bases are the same. What can I do to the exponents? Yes, I can add them together. So 1 plus y minus 1 is just x to the power of y. That's x to the power of y. That looks like there's 2x to the power of y. And what's x to the power of y? 2u. So your proof is done. Yay! Cool. I don't think you need much of my help anymore, right? Because the rest is the same concept. So ultimately, now it's for you to practice. So go ahead. Practice example 4 and 5, and then when you're done, come back and check your answers here. You're going to need this for the next lesson, so I hope you have a good understanding of this topic. All right, begin. Hopefully you know that x over root x is just root x. So this is the same thing as 1/2 with a root x sine y over x. And root x sine y over x is just our original z. So it really just is 1/2 of z, or z over 2. Number 5. Remember, I can write this as x squared plus y squared plus z squared to the power of 1/2. Alright, here we go. Du dz, or sorry, dx. 1/2. Negative 1/2. And then remember, everything else is a constant except for the x, so that's 2x. You'll see there's some nice symmetry in this question. Du dy. 2y 2z and 2's1/2. Goodbye, goodbye, goodbye. So finding this expression now, let's go ahead and square these things. So when I square all of this, so I square, if I were to square that negative 1/2 becomes just -1, so that's an x squared plus y squared plus z squared in the denominator. Don't forget the x also has to be squared, so that's x squared. The next one should be y squared. This is a funky answer. Did you perhaps get x squared plus y squared plus z squared all over x squared plus y squared plus z squared? And if you said this equals to 1, you are correct. If you said this equals to 3, you're not correct, okay? Don't do this. Oh yeah, 1, 1, 1, 1, 1, 1, 3 over 3. Go ahead, don't do that, okay? But in any case, you know, this is just 1. Yay! Alright, I hope this is good. Your next lesson requires you to read some stuff first and then come and try some problems. Please do that. Until next time.